Hello. Apologies. Hello. Today we're going to talk about wave optics, and I'll share my screen. Okay. So I hope I'm audible and visible. Right. So we start with the wave equation. So you've seen the wave equation in the assignment. So what does that actually mean? So the equation that we have, just a quick reminder, it is the wave equation is okay, so y, x, and t is equal to a sine kx minus omega t plus phi. So here, y represents the displacement caused by the wave. Displacement. And a is the amplitude. Amplitude. Now x is the distance along the wave. So it's the distance along the wave. Distance along the wave. T is time, of course. K is called a wave number. A wave number. It's hard to like understand what a wave number is. Wave number is like a spatial frequency. Basically, it's how many cycles per unit length. So the wave number is 2 pi divided by lambda. That's the definition. Okay, phi is the initial phase. Initial phase. So how does that work? Well, if you've done waves in A level, you've probably seen graphs. There are two main types of graphs. You have the displacement time graph. Displacement time graph is the movement of a single point through time. So you think of a wave and you think of a single point on the wave, and the wave goes, well, suppose it goes up and down through time. So like, I don't know, float on the surface of the water, it just goes up and down with the waves. So this is a movement of a single point through time. And the second type of graph was a displacement distance graph. Distance graph. And it also looks like that. But this is like a snapshot or a photograph of a wave at some moment in time. But both graphs are actually graphs of the same function. This is the function. In this case, we say that x is fixed. If x is fixed, the yt, or this function, becomes just a function of time. So y of x and t, if x is fixed, becomes y of t. And here, time is fixed, t is fixed. And in this case, the function becomes a function of x. Does this make sense? Do you understand what I mean when I say when I describe this? Okay. So these two graphs that you've seen, you've encountered, you should have encountered them in your A-level course. And for this graph, this is the time period, t. Whereas here, if you take the distance between peaks, that's the wavelength. And let's play around with this a little. Let's take this equation, just draw a function. Okay, so this is y equals 3 sine 2x minus t. So this is a wave. And now t is fixed at the moment, t is 0. But now I can run the time. So this graph, x is the distance. So this is an x-axis, and this is a displacement. Let's have a look what happens when I start the time. The wave starts to travel. So this is indeed an equation of a traveling wave. Okay. Now, if I change the sign, the wave travels in the opposite direction. So this sign has to do with the speed. Okay. So in fact, the speed of a wave, velocity, the speed of a wave. So it has to be. So if the wave number is 2 pi over lambda, the speed is lambda times frequency. So lambda is 2 pi over k, and frequency is omega divided by 2 pi. Omega divided by 2 pi. 2 pi cancels, and it's omega divided by k. So if you take these, omega divided by k, that gives you the speed of the wave. It's quite interesting to think about it. Okay, therefore, if I change this sign, the wave changes direction. Okay, we can change this sign, and it also changes direction. So, of course. Okay, that's that. Now, let's have two waves. So superposition. Let's have two waves traveling at the same speed. So let's take this wave, and let's take another wave. And let's have it traveling at the same speed, but with different different parameters. So I'm gonna change this to 10, and I'm gonna change this to 15. And I'm going to change this to let's make it 1. Okay. So I have two waves, this wave and this wave. The two different waves traveling at the same speed. Now, if I want to superimpose them, so superposition is when the total disturbance caused by several waves, when two or more waves meet, the total displacement is the sum of individual displacements. So look what happens when I add these two waves. So I'm going to have y equals this plus this. So I get a superposition of two waves. So I get a wave of a different shape. I can play around with the shape a little. I can say, what if I change the shape slightly? So let's say 6. Would that work? 6 and 9. Okay, so this 6 and 9. So now we have this wave and we have this wave, so two different waves. Okay, let's plus 4. So these two waves, when they meet, they produce a wave which looks like this. Okay. Now, of course, probably the most interesting bit is when you have two similar waves, two identical waves, but traveling in opposite direction. So they have the same speed, they have the same frequency, they have the same time period. What happens if we have two waves traveling in opposite direction? It's a question. Do you know what happens? And not quite a line. You imagine a rope, and on a rope, you have two waves traveling in opposite direction. Yeah, of course. So let's have a look. So I'm going to add these two waves. So this is the red one is 3 sine 2x minus 3t. The green one is 3 sine 2x plus 3t. And now this is the sum of the two waves. And you can see that is indeed, it is a stationary wave. It's a wave that does not transfer energy. It has variable amplitude along along. So let's do some calculations and figure out the positions of the nodes. Okay. So what I'm going to do, superposition standing waves. So I've done this. Let's show this mathematically. So you got two waves traveling in opposite direction. So we're going to have y equals sine 3x plus t and y equals sine 3x minus t. And let's add them. Let's call this y1 and y2. Okay, so y1 plus y2 is equal to 3 sine 2x plus 3t plus 3 sine 2x minus 3t. Okay, so there are different ways you can do this. I'll probably go for, I'll just expand, I guess. Expand these using the law of sine of the sum of angles. So that's going to be 3 sine 2x cos 3t plus 3 sine 3t cos 2x plus 3 sine 2x cos 3t minus 3 sine 3t cos 2x. And you can see that these cancel. And I get 6 sine 2x cos 3t. So if you analyze this expression, then this is the amplitude. Amplitude. And this is, well, this is your just oscillation, right? Cos 3t. So it's an oscillation with amplitude 6 sine 2x. So where at which points is amplitude 0? Well, 6 sine 2x equals 0. So sine 2x equals 0. And we know that sine is equal to 0 at 2 points on the circle. So that's 2 pi k, or 0 plus 2 pi k, and pi plus 2 pi k. Or simply put, it's 2x is equal to pi k. Okay. Well, because sine 0 is 0, sine pi is 0. I hope that makes sense. So x equals pi k. So that's 0, pi, 2 pi, etc. And that means x is pi over 2 times k. So the antinodes, sorry, nodes are at x equals 0, x equals pi over 2, x equals pi 3 pi, no, 2 pi, x equals 3 pi over 2, etc. Let's check if that is actually the case. And it is. As you can see, these nodes are correct. You can similarly show that the position of antinodes. Antinodes is when the amplitude is maximum. Okay. At which point is amplitude maximum? Well, you can see that this is the point where the amplitude is this. So 6 sine 2x is equal to 1 or minus 1. 6 sine 2x is equal to plus or minus 1. And, oh, sorry, plus or minus 6, of course, because the maximum value is 6. So sine 2x is equal to plus or minus 1. And we know that it is 1 at point pi over 2 and 3 pi over 2. Or in other words, pi over 2 plus pk. So 2x is pi over 2 plus pi k, sorry. Pi k, and x is equal to pi over 4 plus pi over 2k. So this is the position of antinodes. Let's check if that is actually the case. Well, yes, it is pi over 4, 3 pi over 4. Yeah, so 3 pi over 4, 9 pi over 4, etc. So you can easily, if you substitute k equals 1, you get k equals 0, you get pi over 4. Then you get 3 pi over 4. Then you get 5 pi over 4, etc. All right. Does that make sense? Does that add a new level of understanding of standing waves? Oh yes, it would be valid, of course. Yeah, you could find the distance between two nodes. That's perfectly acceptable. Yeah, but um, I'm doing it from here. So the interesting thing, like I don't know, it really fascinates me. So then this is maybe this is just me that this is the amplitude and this is the thing. So if you draw, it's like a wave. So this is your amplitude, and then between each points, you have oscillation up and down um, between yeah. Well, that's what a standing wave is. Anyways, moving on. Talking about interference. So thin film interference. So if you take two pieces of glass and put them at a very, very small angle, they need to be very close to each other. They're thin pieces of glass. You will see that the light, there's a light falling onto the glass, um, enters the glass, reflects from the bottom surface of the first piece of glass, and exits the glass via this path. But some of the light actually passes through the glass and reflects from the second piece of glass and enters. And these two rays of light, one and two, they they are coherent. They have similar well, they have the same frequency, and they interfere. And they interfere, producing a maximum or a minimum or anything in between. So it doesn't have to be a maximum or a minimum. But yeah, you have interference between the two rays of light. Now, if you make the gap slightly bigger, you have a different path difference. So 1 and 2 have path difference equal to double the size of this gap, h, 2h. And 1 dash and 2 dash, this is h dash, have path difference 2h dash. Now, because white light consists of various wavelengths, so white light has a variety of wavelengths of wavelengths. Different colors require a different gap to produce um, constructive interference. interference. And that's what you see. Um, you see that for this part of the glass, you have a red light constructively interfering, and then there's a green light, etc. So that's why you have this separation of colors. Okay, so you at different widths, at different gaps, different size of the gap produces a different um, produces interference of a different color. And of course, because the glass is not perfectly uniform, you see these interesting patterns. Or perhaps the glass is under tension. If the glass is under tension, then it could be thinner somewhere or thicker, or yeah, you have a different that affects the path difference. Okay. Yeah, so that's what I wanted to talk about. Another similar effect, it's not the same, but similar, it's called photoelasticity. So photoelasticity is when you shine shine polarized light onto a piece of plastic, or you just analyze light from through a polarizer. If you take some polarizing glasses and look at a piece of glass, you will see these patterns. So these patterns are stress inside the material. So this stress comes from the manufacturing process because the plastic is made initially is liquid, and then when it solidifies, it has some stress. It produces stress when it solidifies effectively because it shortens. And you can see those stress patterns inside materials, which is quite fascinating. This is one of the ways how engineers, when they design, for example, they design a new bridge or a new building, they make it out of a transparent material. They make a model of a transparent material and see what happens. They analyze it through some polarizing filters. Okay. Moving on to problem 5. So this is Newton's rings. Newton's rings. So this is one of the problems from the assignment, and you need to find the relationship between the distance from the center to the uh, well, yeah, the distance to the center to the number of the dark ring. So the pattern that you see, so Newton's rings. Newton's rings. So you will see patterns like this. Oh, this is better. Okay. This is the pattern that you would see looking from the top. So a lens is placed on a glass plate, and you have light in the first instance. Light is coming in, reflecting from the inner part. Ooh. Uh, a phase change when later from the top surface of the plate, but not at the lower surface of the lens. Yes. So you have reflection from the lower surface of the lens. Okay. You have a reflection from the lower surface of the lens, and then you have a reflection from the glass plate as well. And these two rays, they interfere. The curvature is very slight. Yes, so the radius of curvature is very slight. So um, there you don't notice that the reflection is in a slightly different direction. So if you're wondering why light ray comes in, why doesn't it reflect that way? Well, because the curvature is really made to look bigger than it actually is. So yeah, you have light reflecting from the lower surface of the lens and the glass plate, and these two rays interfere. And so if you take the if you find H, you can say, okay, this is the radius of the curvature of the of the glass, and then this is small h, so you can say, well, this angle is theta. So you can say that, let's make a bigger diagram. So you have the radius here, the radius here. Now this line, and if this angle is theta, then you have this line. This is r cos theta. And here, this is h, and this is small r. But at the same time, you can say that small r is r sine theta, and h is equal to r minus r cos theta. Now, because theta is very small, you can sine theta is approximately um, what is it? Is approximately theta, and cos theta is approximately 1 minus theta squared over 2. And we substitute that in. So we take this, take this, and here we have r equals r theta, and we have cos okay, so h is equal to r minus r multiplied by 1 minus theta squared over 2, which is r theta squared over 2. But r theta is r. So here we can write r theta multiplied by theta divided by 2. So that's, well, actually, no, that doesn't make any sense. I'd rather do, from here, I say theta is r over r, because we don't know theta after all. And then we have h is equal to r multiplied by r squared over 2r squared. And so it's r squared over 2r. And I think that's exactly what they got. 2rh, yes, is r squared. That's exactly what they have. 2rh is r squared. Now the path difference between the two rays, because we know that we have one ray reflecting from the bottom surface and one ray reflecting from the mirror, the path difference is 2h. Path difference is 2h. But there's a catch, and the catch is that when you reflect off when it's a hard reflection. So what does a hard reflection mean? A hard reflection is when you reflect off a material with higher refractive index. So if you are traveling through the air and you reflect from glass, that's a hard reflection. There's a change of phase. This can be demonstrated um, using FET waves on a string. So if I have a fixed end and I reflect off this end, there's a change of phase. So the phase changes to the opposite. The wave was up, now the wave is down. So that's what we call a phase change. So hard reflection, change of phase. So uh, hard reflection. I call it hard reflection. I'm not sure it's the proper name for it, but um, now it's a loose end. A loose end means the rope is not attached to anything. That's what I call a soft reflection or a reflection from a loose end, open end. And you can see there's no phase change. No phase change. And that is, well, this is fascinating, of course. So hard reflection, phase change is pi. The phase change is pi, and so open end reflection, soft reflection, no phase change. Okay, so from the mirror, from the glass plate, sorry, it's a hard reflection, so there's a phase change here. However, there's a no phase change here because you're reflecting off, well, the boundary with air. Okay, and that means that for a bright ring, this has to be true. So it has to, for a bright ring, 2H has to be 2H has to be 2m plus 1 lambda over 2. And therefore, but H is r squared over 2r. So r squared over 2r equal to 2m plus 1 lambda over 2. And I think that's exactly what we have, except the 2. Where's the 2 gone? The pattern difference is 2h. Oh, h is, of course, h is r squared over 2r. Okay, so it's like this, 2, and 2 cancels out. All right, so that is the condition for a bright spot, bright ring. And if you have 2h is equal to m lambda, that's a dark spot. So that's 2 times r squared over 2r. So equals m lambda. In other words, that is a dark ring. Okay, I hope that makes sense. Do you have any questions about this? Okay. Problem 6. That's a very nice one. So you have a source of light, here. Then you have two mirrors, mirror 1. Okay, you should see the question. A mirror and another mirror. And this screen is K1, and this small screen is K2. And there's a detector, D. This is the detector that moves up with the velocity V. So the detector is moving. What's going on? Well, the light from the source takes two different paths. And whenever you have two different paths, you immediately jump, ooh, it's path difference. Of course there is. So there's a path difference between this one. This is path 1. And there's path 2, which is this. Path 2. Path 2. And there's a path difference between them. And if the path difference, if delta, how do we call it? Delta x is, do I want to call it delta x? Okay, delta x, path difference. If delta x is equal to m lambda, that means it's going to be a bright spot. And if delta x is 2m plus 1 times lambda over 2, that's a dark spot. But it's a little bit complicated to think about it, like especially if we don't know um, the position of S, right? Don't know the position of S, but what's interesting is that we can construct an image of S. So we have S1. So S1 is the image of S. And S2 is also an image of S in lower mirror. And S2 is the image of S in the upper mirror. S2, the image of S in upper mirror. All right, so realistically, light is coming from S1 and S2. Like if you were sitting at D and looking, you would see two sources. You would see two copies of the same source, one slightly to the left and one slightly to the right. You would not see S because S is blocked by the screen. So what you see standing at D, you see two sources of light. And all you need to do is rethink this problem in a different in a different point of view. Now, if you if you think about it, mm, let's call this d1, and that means that this distance is also d1. If this distance is d2, then this distance is also d2. So the total distance from S1 to S2, apologies, I've got a young physicist. Wow. Yeah. Oh, yeah. So S1, S2, S1, S2 is equal to 2d1 plus 2d2, but d1 plus d2 is d, but d1 plus d2 is d, which is the distance between the plates. And therefore, S1, S2 is equal to 2 multiplied by d1 plus d2. That's equal to 2d. Right. So on the screen, we have an interference pattern. The screen will see an interference pattern produced by the two different paths of the light from the same source. And we can use the formula that you know from A level, right? So we have the width. So oh, the width between two bright fringes, W, W is equal to the length L, the distance from the source to the screen, multiplied by the wavelength. If you use a bigger wavelength, there's going to be a bigger gap, which will be divided by, well, the distance between the two sources, which is, well, 2D. Okay, and then therefore we can find, yeah, the gap. The question is, a detector is moving along the screen with speeds of 0.1 millimeters per second. Okay, find the frequency of the output signal from the detector. So we need to find the frequency here. So the detector will go through minima, and maxima. So therefore it will have a smaller and bigger amplitude of the signal coming in. So we're going to use that. So frequency is 1 divided by the time period. And time period is the time between two peaks. Time between peaks. So t is equal to w, is the distance between the peaks, divided by the speed. Okay, so the frequency is going to be 1 divided by t. That's going to be v divided by w. So frequency that we need is speed, v, divided by w, which is L lambda, multiplied by 2d. And now we can finally get the answer. So it's 0.1 times 10 to the minus 3 meters per second, multiplied by 2d, so 2 times 0.03 meters, divided by L, which is 1 meter, divided by 600 nanometers times 10 to the minus 9. And that will be 0.1 10 to the minus 3 times 2 times 0. So that's meters. So meters cancel. 1 meter. Meter cancels, and we got inverse seconds. Times 2 times 0, 0.03 divided by 600 times 10 to the minus 9. 10. Oh, wow. 10 hertz. I did not expect that answer. Okay. Yeah, so it will go through 10 peaks every second, which is quite nice. Now the reason why the peaks, when if you did experiments in school, you did the experiments and the peaks were quite wide, right? There was certainly a few millimeters. But here the problem is that the sources are 6 centimeters apart. So it's like a double slit with the slits being 6 centimeters apart. So it's quite a significant difference. Okay, so that's problem 6. And finally, two very similar questions, and it's about angular resolution. So when light comes through an aperture or an opening, it diffracts. So if you have an opening of size d, the size of your aperture, and let's say you have a distant object like a star, and this is a screen. The light from the star will go through the opening, but because it goes through a small gap, it will diffract because these are waves, right? It's very easy to demonstrate. So ripple tank. So stopped. Single slit. So this is an opening, and you have light coming in. And you can see that the intensity of light produces the waves produce a diffraction pattern. And if you were to draw the intensity, if you were to draw a graph of intensity this is displacement and vertical is intensity, then the graph would look like this. So we have peak intensity here, minimum intensity here. That's a dark spot, bright spot, dark spot, bright spot, dark spot. So it will go dark, bright, dark. Okay, so this is a diffraction. So on the screen, you would see a diffraction pattern. Produced by the light coming from that star. If you take another star, so this is the diffraction pattern from star 1, S1. This is S2, star 2, another star. And the light comes through the aperture, the objective, and it also produces a diffraction pattern. I'm just going to copy that. Right. Now, if the star 2 was closer to the star 1, the two diffraction patterns would overlap, and the two stars would be indistinguishable. And if they don't overlap, well, at least this is the minimum separation. Then you can distinguish two bright dots. So basically, do you see two dots or do you see a single splodge? Yes, single blob of light. That's the difference. So your eye, your pupil has size, it has an opening, and when you look at an object, what determines whether you can see something or not is their angular separation. So we say that this is theta, is the angular separation. The separation. Okay. And angular resolution is the smallest angular separation that you can determine from well, we're using your device. If it's an eye, it's maybe 2 millimeters. Does that make sense? Do you understand what I'm talking about? Okay. So the angular separation, smallest angular separation, is approximately equal to lambda over d. And that brings loads of really fun questions to talk about. And the first one, like both these questions were given to me in university was when I was in year 1. What diameter of lens do you need to read a newspaper from low Earth orbit? Could easily be a university interview question. It's like, okay, so you got to imagine yourself. So there's a newspaper somewhere. Yeah, assuming the newspaper is at sea level. Yes. So the newspaper is at sea level. You're in low Earth orbit. So low Earth orbit, I'd say probably 100 kilometers. That's the lowest you can go, because anywhere less than that, you would slow down very quickly because of the friction with the air. So you have some sort of satellite with a huge telescope, and maybe it's a spy satellite, and you want to read today's newspaper from orbit. So you want to know the diameter of your telescope, and well, in order to see what's going on, in order to read a letter, the you should be able to distinguish the top and the bottom of the letter. So I'd say a generous 1 centimeter. So you want to be able to see an object of size 1 centimeter. And your angle theta is this, d delta theta. And this is 100 kilometers. So the delta theta is approximately 1 centimeter, so 0.01 meter divided by 100,000 meters, so which is approximately 10 to the minus 8 radians. That's the angular resolution that you need. And then you just use the formula. Well, the wavelength, well, we assume 515 Newton meters. So assuming you're using green light, which is the mid-range. So that means assume lambda is approximately 550 nanometers. So the diameter of the telescope is lambda divided by delta theta, which is 550 times 10 to the minus 9 divided by 10 to the minus 8. And this should be approximately what? 55 meters. Okay, so yeah, that's probably the biggest optical telescope ever built, especially if we're talking about orbit. So yeah, definitely unreasonable to assume you would have such a lens. And the other problem, also, I don't know, is just a fun problem, or even a funny problem. Astronauts have landed on the moon and to inform that the landing was successful, they decided to unroll a large piece of black cloth on the surface. Well, assuming the radio doesn't work or something, so they have no way of telling the Earth that the landing was successful. So they have a large piece of black cloth. What is the minimum size of the cloth if it's to be seen through a 1 meter telescope from Earth? So 1 meter diameter, of course. So you have a telescope, which D is 1 meter, and you have a cloth of size X, let's say, and you want to be able to see that piece of cloth from the Earth through a telescope. So you want to know this angle, and the distance to the moon is approximately 380,000 kilometers. So similar situation. The delta theta is x over L, is approximately x over L. It's a very small angle, so you can use this approximation. And then you have to say, well, okay, delta theta on the other hand, that's equal to lambda over d, which is approximately lambda over d. And therefore x is approximately lambda times L over d. Same assumption. Lambda is 550. So 550 times 10 to the minus 9 meters multiplied by 380,000 380 million meters and divided by d, which is 1 meter. So this is not that big. Well, it is very big, but not. Doesn't seem it's going to be crazy big. 380,000. 209 meters. 209 meters in diameter. So I'm assuming it's a chunk of cloth. 209 meters, like 2 football fields. Okay, I hope that was useful. I hope that makes sense. I do advise you to play around with this Desmos tool and just try to see what happens when you try to add waves. An interesting one happens when you try to do waves of different if you try to add waves at different speeds. So let's say one of the waves is slower than the other one. So you can see, let's speed it up. So for example, speed is omega divided by k. So I need to increase omega. So let's make this 12. So you can see those interesting patterns going on. So it's one wave traveling through the other one. So minus 12. So yeah, so we have 2 waves, but one is faster. So you see quite an interesting pattern here. and it's still yeah. So now if you take standing waves, actually, um, if you take two waves traveling in the same direction, three, and they have 2x minus 3t. So this is just the same wave twice, but if you change 3 to, I don't know, 3.5, you can see that the wave grows, and then the amplitude. So it's a traveling wave, but the amplitude varies. These are called beats. Beats. And this, I like to demonstrate it like this. So if you have y equals sine 3x, and you have y equals sine 3.1x, 3.3, 3.5. Yeah, that's better. So you have waves of similar frequency, but not quite. So sometimes they are in phase, sometimes they're out of phase. And when you add them, y equals sine 3x plus sine 3.5x, you see a pattern like this. So yeah, this is called beats. And when you have changing amplitude, because you have a picture like this. Amazing. So I'll leave you here. Yes, sine, of course, because look, when we talk about waves, the question was can you use cosine instead of sine? Do you remember when I started, I said there's a phase here. So all you need to do is to make the phase minus pi over 2. No, phase. Yeah, minus pi over 2. If you make, if phase is minus pi over 2, uh, look what happens. You know what? Sorry, I'll just. If phase is minus pi over 2, it's going to be y x t equals a sine kx minus omega t minus pi over 2. And that's equal to a sine kx minus omega t multiplied by cos pi over 2. I'm opening the brackets, and that's then minus a cos kx minus omega t multiplied by sine pi over 2 y minus. It shouldn't be minus. I think I need to say plus pi over 2. Plus pi over 2. Yeah, sorry, plus pi over 2. And then I say then this becomes plus. So then this thing is 0, and the whole thing becomes this is 1, a cos kx minus omega t. So you can see all you need to do is just use phi equals pi over 2 to get cos. So sine and cos are the same thing, you just shift it, right? Because if you shift the cosine graph by pi over 2, you get cosine graph. Okay. Yeah, you're welcome. I'll see you in 2 weeks' time for the next webinar. There's only 2 webinars to go, and I'll see you.